Continuous time Fourier Transform. Understanding the CTFT. Representation of an aperiodic signal. To better understand the nature of the Fourier transform representation, we start by revisiting the Fourier series representation of a continuous time periodic rectangular pulse, focusing specifically on a single period. Fourier coefficient derivation. Step 1. Compute the integral. Step 2. Apply limits. Step 3. Simplify exponents. Step 4. Use Euler identity. Next, we apply this result to the last expression. Step 5. Simplify. Step 6. Final form. Step 7. Sync representation. The expression can be rewritten as special case n equals 0. Final result. Cn as samples of an envelope function. That is, with omega thought of as a continuous variable, the function tau times sinc of omega tau over 2 represents the envelope of t times Cn, and the coefficients Cn are simply equally spaced samples of this envelope. Also, for a fixed tau, the envelope of t Cn does not depend on the period t. The top figure shows a continuous time periodic rectangular wave, where t equals 1 and tau equals 0.5. The bottom figure shows the corresponding envelope function for this fixed tau, along with the sampling frequency associated with a pulse train that has a period of 1. As we increase the period of the pulse train to t equals 2, the pulses move farther apart in time. At the same time, the sampling in the frequency domain, corresponding to the Fourier coefficients, moves closer together, in the same proportion. In the case where the period is t equals 4, the spectrum becomes 4 times denser compared to the base case, where t equals 1. This behavior can be clearly observed in the animation. Following the same process, the period t can be increased indefinitely. As this happens, the spectrum becomes progressively denser, eventually approaching a continuous function as t tends to infinity. In particular, consider a signal x of t that is of finite duration. That is, for some number tau over 2, x of t is equal to 0 if absolute value of t is greater than tau over 2, as illustrated in figure at the top. From this aperiodic signal, we can construct a periodic signal x tilde of t for which x of t is 1 period, as indicated in figure at the bottom. As we choose the period t to be larger, x tilde of t is identical to x of t over a longer interval, and as t approaches infinity, x tilde of t is equal to x of t for any finite value of t. Let us now examine the effect of this on the Fourier series representation of x tilde of t. Suppose that x tilde of t has a Fourier series representation, then we have the synthesis and analysis equations carried out over the interval minus t over 2 less or equal to t and less or equal to t over 2. Since x tilde of t is equal to x of t for absolute value of t less than t over 2, and also, since x of t is equal to 0 outside this interval, the analysis equation can be rewritten as follows. Therefore, we define the envelope x of j omega, corresponding to tCn, as follows. We have, for the coefficient Cn, Then, we can express x tilde of t in terms of x of j omega as. Or equivalently, since 2 pi over t equals omega 0. As t tends to infinity, x tilde of t approaches x of t, and consequently, in the limit the last equation becomes a representation of x of t. Furthermore, omega sub 0 tends to 0 as t tends to infinity, and the right-hand side of that equation passes to an integral. Therefore, we have. The equations are referred to as the Fourier transform pair. With the function x of j omega referred as the Fourier transform or Fourier integral of x of t. And the function x of t referred as the inverse Fourier transform equation. And be not conformed to this world, but be ye transformed by the renewing of your mind, that ye may prove what is that good, and acceptable, and perfect, will of God. Romans 12 verse 2.